Hello, thanks for tuning in. I'm Daniel Stern. I'm speaking to you from the University of Chicago, or rather from my apartment a few blocks away. And this is for the virtual workshop on Ricci and scalar curvature in honor of Misha Gromov's 75th birthday. All right, so I want to quickly thank the organizers for inviting me to participate, and also for having the foresight to plan a virtual workshop well before we knew what the summer of 2020 was going to be. All right. So I'm going to talk to you today about scalar curvature and its relationship with harmonic functions and some related objects. All right. So the broad motivation for the work I'm going to tell you about is, I think, motivation that's shared with a number of other talks in this workshop, which they're interested in this old question about understanding how lower bounds on scalar curvature constrain the topology or somewhat vaguely the large-scale geometry of a given Riemannian manifold. All right, and really I'm interested in the following big sub-question, which is how the lower bounds on scalar curvature influence the existence or the shape of solutions to natural geometric PDEs and variational problems on our manifold. All right, and this is really a crucial sub-question because answers to this provide our toolkit for studying general questions about scalar curvature, right? So if we want to understand the relationship between scalar curvature and topology, well, then it might help, for instance, to know how scalar curvature relates to stable minimal hypersurfaces. And then we know that, well, certain types of non-trivial topology force the existence of certain interesting non-trivial stable minimal hypersurfaces. And then those stable minimal hypersurfaces provide a bridge between information on the scalar curvature and information on topology. Right? So this is a familiar principle in geometry. But for scalar curvature, compared to things like Ricci curvature, we don't have that many arrows in our quiver. Right? So let's compare Ricci curvature. So for Ricci curvature, starting in the early to mid 20th century, we have many tools understanding how it relates to various PDEs, right? So for instance, we know how it relates to geodesics, to minimal hypersurfaces, again, through stability, through the Bachner formula, we know how it relates to harmonic one forms, harmonic functions, other elliptic equations. Again, through Bachner, we know how it relates to heat flow and other scalar parabolic equations. More recently, people have looked at how it relates to optimal transport. The point is there are many tools we can use to probe the effects of Ricci curvature. Okay, so to provide a simple illustration to this, I want to go back to the spring of 2015, to my general exams, first year of my PhD, okay, and recall a fun question from the geometry section. All right, so the question was to provide, or the problem was to provide 3 proofs of the following statement. So if we have a closed oriented N manifold with positive Ricci curvature, we want to show the degree 1 cohomology with integer coefficients vanishes. Okay, that's the statement. So let's provide our proofs in chronological order. So if we go to the early 1940s, then we can use the Bonnet-Myers theorem. Okay, so in particular by exploiting the relationship between Ricci curvature and energy minimizing geodesics, we know that if we have a complete manifold with the positive lower bound on the Ricci curvature, well then in fact, even if it's a priori non-compact, there's an explicit diameter bound. So in fact, it has to be compact. And if we apply this to the universal cover of the manifold we're starting with the lifted metric, well then we see that our universal cover has to be compact. So immediately, it follows that whatever the closed manifold we're starting with was, its fundamental group has to be finite. Okay, so pi 1 of m is finite. Well, by Hurevich, we know that the degree 1 homology with integer coefficients must then also be finite. In particular, it's all torsion. So the first Betti number vanishes. All right, but if we recall now our universal coefficient theorem, then we can see that, well, the degree 1 cohomology with integer coefficients is isomorphic to the torsion-free part of our homology. So in particular, since the first Betti number vanishes, the degree 1 cohomology with integer coefficients has to vanish. All right, and that's our first proof. And here, of course, what Bonnet-Myers gives us is much stronger than the conclusion we were after, right? It tells us that the fundamental group is finite, rather than this weaker conclusion that this degree 1 cohomology vanishes. All right, so that's our geodesic approach circa 1942. All right, so if we move up a few years to 1946, we can apply Hodge theory, and really we can use this Bachner technique. Right, so if we want to study more directly just this cohomology, well, we can say, okay, so we know that this degree 1 cohomology, we just remember that it was torsion-free, right, with integer coefficients. Okay, so in particular, if we want to show that it vanishes, Well, it's enough to show that degree 1 cohomology with real coefficients vanishes. And in particular, it's enough to show that the de Rham cohomology in degree 1 vanishes. So in particular, every closed 1 form is exact, right? Right, but now we can appeal to Hodge theory. So Hodge theory tells us that, well, in any de Rham cohomology class, we can find a representative that minimizes the L2 norm. Okay, and this is going to satisfy this harmonic condition where, in addition to being closed, which of course it is to belong to the cohomology, right, it's also co-closed, it's divergence-free. All right, so with this nice elliptic system. And then Bachner comes along in 1946 and tells us that, well, for such a 1 form, if we take the Laplacian of half of its norm squared, then this is going to be something like the Hessian squared, or rather d of this 1 form squared, plus Ricci curvature in the HH direction. Okay. So now, if Ricci is positive, we can integrate this formula or apply maximum principle, take your pick, to conclude that if Ricci is positive, no such 1 form, no harmonic 1 form can exist. Right? But then this tells us by Hodge theory that the de Rham cohomology has to vanish. Okay, and in particular, H1 with integer coefficients has to vanish as well. So that's proof number 2 via Bachner technique. All right, well, let's go to door number 3. I'm not sure exactly when to date this, but we can use minimal surfaces. All right, so by Poincare duality, we know that this degree 1 cohomology with integer coefficients is isomorphic to the codimension 1, so the dimension n-1 homology with integer coefficients, right? So in particular, the given question is equivalent to showing that positive Ricci curvature forces the codimension 1 integer homology to vanish. Okay, so that's what we're after. Well, if we have a non-trivial codimension 1 homology class, and the tools of geometric measure theory, so in particular results by people like Federer and Fleming and Jim Simons and others, tell us that any such class contains an area minimizing representative. So there is a stable two-sided minimal hypersurface, which is going to minimize area among all of the representatives of this homology class. Okay, and that hypersurface can have a small singular set if we're in higher dimensions, but for applications to Ricci curvature, that turns out not to be significant. Okay, so we'll just ignore that for now. All right. So if we have a stable two-sided minimal hypersurface, what can we say about it? Well, by virtue of its being minimal, the first order condition tells us that the mean curvature vanishes, of course. But then testing the second variation, the stability, we know that in fact we also have to have this following inequality, right? So if we test any test function phi on our manifold, well, if we look at its Dirichlet energy along the hypersurface, minus the second fundamental form squared plus Ricci in the normal direction, multiplied by this test function squared, that's always going to be a non-negative quantity, right? This Hessian is non-negative. Okay, so in particular, we can take phi to be 1. All right, and then this Dirichlet term drops out. And if Ricci is positive, this is going to be a positive term over here, right? This integrand is positive. So what this tells us is that as Ricci is positive, then in fact we can't have a non-trivial, stable, two-sided minimal hypersurface. Okay. So in particular, we conclude that this codimension 1 homology has to vanish. Okay. So multiple different paths to the same result about the cohomology vanishing. All right, but each path comes with some pretty different information about how the Ricci curvature is actually interacting with the geometry. All right, but now let's get back to scalar curvature. Okay, so if we're talking chronologically about the important developments in scalar curvature, and I'd start with Lishnerovich's observations relating it to the Dirac operator in the 60s. But instead, we're going to jump around a bit and note that this latter approach to studying Ricci curvature, using stable minimal hypersurfaces, turns out to be useful for scalar curvature as well, right? And this is this key insight of Shane and Yao in the mid to late 1970s, okay? And the insight really hinges on the following cute computational trick, which is that this Ricci nu term that shows up in the stability inequality, well, we can rewrite it via the Gauss equation, okay? And if we rewrite it, we see that we can express it as half of this quantity, the ambient scalar curvature of our manifold, minus the intrinsic scalar curvature of this hypersurface with the induced metric from the embedding, right? And then plus, well, if we're working with a general hypersurface, we have this mean curvature squared, obviously for minimal, that drops out. And then minus the second fundamental form squared term. Okay, but since that second fundamental form squared comes with a half out front, when we plug this into our stability inequality, we still have a half second fundamental form squared here, plus ambient scalar curvature minus the intrinsic scalar curvature for that hypersurface, right? So in particular, whereas positive lower bounds on Ricci would preclude the existence of two-sided stable minimal hypersurfaces, then even before digging into this, we see that positive scalar curvature won't rule out the existence, but it'll tell us something about the intrinsic geometry of that hypersurface, right? Where this intrinsic scalar curvature is now coming into play. Okay, and of course the first big success of this technique was the resolution of the Garrosh conjecture, showing that T3 admitted no metric of positive scalar curvature. Okay, and of course what they proved is much more. Using sort of a mapping approach to minimal surfaces, they showed that in fact the manifold has positive scalar curvature. It admits no incompressible minimal surfaces. Here I'm quoting a less refined version of that, where we're using sort of a homological approach, mirroring what we were doing for this Ricci positive result, right? So if we just are looking at area minimizers in a homology class, we can prove the following theorem with Shane-Yao's technique. So if M is a closed oriented 3 manifold of positive scalar curvature, then every class in H2 can be represented by embedded 2 spheres, every class in H2 with integer coefficients, right? So in particular, if we think about the 3 torus, well, it has lots and lots of homology, it has a rich homology, but none of those classes can be represented by 2 spheres. Okay, so in particular, this rules out positive scalar curvature on the 3 torus and many other manifolds. Okay. All right, so how do we go about doing this? We start out the same way we did for this Ricci positive result, right? So we say, okay, if we have a non-zero class in integer homology in codimension 1, then we can take an area minimizing representative, and since we're working with integer homology in an oriented manifold, this is going to be a stable two-sided minimal surface. All right. Well, now we can play with this rearranged stability inequality we have, right? And if we plug in the test function 1, so we're looking at what happens when we flow our surface by speed 1. All right, then stability tells us that half of the integral of second fundamental form squared plus the ambient scalar curvature of our 3 manifold minus the induced scalar curvature on our surface, all of this is non-positive, okay? But in particular, if we think back to our curves and surfaces or whatever, then we note that, well, half of this intrinsic scalar curvature on our surface is just the sectional curvature or the Gauss curvature. And so its integral is going to be 2 pi times the Euler characteristic, right? So Gauss-Bonnet together with stability tells us that half of this integral of the second fundamental form squared plus the ambient scalar curvature is bounded above by 2 pi times the Euler characteristic. So in particular, if the scalar curvature is positive, then this sigma has to have positive Euler characteristic. And moreover, if this is a homological area minimizer, well, that has to be true of each component, right? So it holds true not just on for the total Euler characteristic, but this holds for each component of this minimal surface, right? So in fact, the whole thing is a union of spheres, and therefore it follows that for any given homology class, we can represent it by a union of spheres just by minimizing the area, right? So that proves the theorem stated here. Okay. So they were then able to extend this approach to higher dimension. Now the relationship is a little more subtle. And so you're using the stability inequality to say things about the conformal Laplacian of the stable two-sided minimal hypersurface, or to say things about warped product metrics on the surface product of S1. And this somehow allows you to build up this induction on dimension, to build up your library of manifolds which don't admit positive scalar curvature. Okay. And of course, one of the crowning achievements of this minimal surface approach of Shane and Yao is their proof of the Riemannian positive mass theorem, okay, which for dimension 3 goes back to the late 1970s, for dimensions up to 7 around the same time, and then only very recently they finished off sort of this approach for working around singularities of area minimizing surfaces in higher dimensions to extend it to arbitrary dimensions. This just within the last 5 years or so. All right. And then, of course, I've skipped over this whole story about Dirac operator techniques for studying the scalar curvature. That's another massively important story. I assume there will be lots of talks in this workshop dealing with that in more detail, right? But this begins with Lishnerovich in the 1960s observing this Bachner-type relation between Dirac operators and the scalar curvature for harmonic spinners, and then this is built up further by people like Atiyah and Singer, Hitchin, And then Gromov-Lawson finds some interesting twists on this technique, which allow you to get spinor-type proofs of the Gauroche conjecture and these sorts of things. All right, but really these two techniques, the minimal hypersurfaces and the Dirac operators, have kind of dominated the story of scalar curvature for many years now, with some very notable exceptions, like, for instance, the inverse mean curvature flow in dimension 3. Okay. But now let's get a little naive. All right, so let's return to this second proof of this fact that the Ricci positive implies no integer cohomology rather in degree 1, right? Okay, so here we're using the Bochner technique. Right? We said if Ricci is positive, then M carries no non-trivial harmonic 1 forms. That was the key observation. Well, if we're thinking by very naive analogy with the results we had for stable minimal hypersurfaces, so there we saw that Ricci positive ruled out the existence of two-sided stable minimal hypersurfaces, right? But that lower bounds in the scalar curvature didn't rule out their existence, but told us something about the geometry. So a very naive question one could ask is whether something similar is true for these harmonic 1 forms. Okay, so in particular, while positive scalar curvature certainly doesn't rule out the existence of harmonic 1 forms, take S2 cross S1 for instance, right? Does it provide some constraints on their shape, like it does for the stable two-sided minimal hypersurfaces? Okay, more precisely what I mean here is the lower bounds in the scalar curvature constrain the intrinsic geometry, or in particular the topology, of this codimension 1 foliation of M by hypersurfaces that are going to be perpendicular to a harmonic 1 form. Right? So that's the basic guiding question. Okay, and in dimension 3, the work I want to talk about today is a positive answer. So yes, there is some information along these lines, at least in dimension 3, and we're going to explore the consequences a little bit. Okay, but before we start stating theorems, let's lay out our tools a little more carefully. All right, so let's say we're on a closed-oriented n-manifold to start. Later we'll specialize to n is 3, right? Then we have our old friend Poincare duality telling us that the codimension 1 integer homology is isomorphic to the degree 1 integer cohomology, right? And if we remember something about Eilenberg-MacLane spaces, you might remember that these are both isomorphic naturally to the group of homotopy classes of S1 valued maps from M, where we're thinking about S1 as R mod Z, and the group action here is just addition, okay, in R mod Z. All right. And if you don't like Eilenberg-MacLane spaces, well, you're still in luck because these isomorphisms are very easy to see geometrically, right? So in particular, if we want to send a homotopy class of maps to S1 to codimension 1 integer homology class, all we do is take level sets. So you have a homotopy class of maps, you take your favorite smooth representative, you take a regular level set, boom, the homology class of that level set is precisely the homology class you were looking for in Hn-1, right? So it's a very straightforward map from this guy over here to this one on the left-hand side. All right. Similarly, there is a very obvious map from homotopy classes of S1 valued maps to the de Rham cohomology, right? Where given a map, you again take your favorite, or given a homotopy class, again take your favorite smooth representative, look at this gradient 1 form, so the pullback of dt from R mod Z, and then this is a closed 1 form. It has a de Rham cohomology class. Okay, and it's not hard to see that this is a nice injective map. Okay, so this gives you a way of viewing your degree 1 integer cohomology as a lattice inside the de Rham cohomology. Okay, so in particular, if you aren't a fan of the universal coefficient theorem, this is another fun way of seeing that this degree 1 integer cohomology is torsion-free. Okay, but these are somehow the geometric ways of realizing some of these isomorphisms, at least some of the geometric ways. All right, so in particular, if we're thinking about this problem of minimizing Dirichlet energy in the given homotopy class of S1 valued maps, with this identification in mind, it's not hard to see that it's equivalent to the problem of minimizing the L2 norm of the gradient 1 form in the associated de Rham cohomology class. Okay, so in particular by Hodge theory, well, we know we can always minimize L2 norm to get a harmonic 1 form. And then since this is going to have integral periods, we can integrate it to get a nice S1 valued map, which minimizes energy. So in particular, every homotopy class of S1 valued maps contains a nice energy minimizing representative whose gradient 1 form is harmonic in the standard Hodge sense. Okay, so these harmonic maps to S1 we can really just think about them as giving us a nice lattice inside the space of harmonic one forms. Okay, so in contrast to other harmonic mapping problems, where the problem is highly nonlinear and more interesting analytically. So in particular, given any codimension 1 homology class, well, we saw before that we can always represent it by an area minimizer, right? But we can also, if we want, find a nice harmonic map to S1 whose fibers all represent this class, okay? Just by this energy minimization procedure in this dual homotopy class of S1 valued maps, okay? And so per this discussion we were having before, we're interested in understanding how scalar curvature affects the geometry of those fibers. All right, and to this end, we have the following identity, which I noticed about a year ago now, which tells us that if we have a closed-oriented 3 manifold, now we're specializing to dimension 3, and we have a non-constant harmonic map to the S1, then what do we have? Well, we have that the average Euler characteristic of all the fibers, where we have this 2 pi in front for reasons you can probably anticipate, this is going to be an upper bound for the average over all the fibers of the integral over each fiber of this half of this weighted Hessian squared term, which might remind you of a second fundamental Porte squared term, plus the ambient scalar curvature. All right, and you can also reformulate this as an integral on the manifold itself, right, just by plopping a norm du out front by the co-area formula. Okay. So in particular, if you're just thinking about the minimal surface picture, this might remind you of an averaged form of this identity we had for stable minimal surfaces in 3 manifolds by plugging in speed 1 to the stability identity, right? So, so this is kind of reminiscent of what we had there. And right away I should note, okay, so I'm starting to talk about the geometry of these fibers. Well, of course, not all of these fibers will be smooth, right? In general, this map will have critical points. The geometry will be singular at those critical points. The topology of the fibers will change as we pass through those critical points, which is why we have to talk about the average Euler characteristic as opposed to one single Euler characteristic. But okay, at least by Sard's theorem, right off the bat, we know that almost every value is a regular value. So for almost every t, these quantities make sense, right? And okay, to actually show though that these integrals make sense, that these relevant quantities are integrable, for that, that will fall out of the derivation of the identity. Okay, but at least these make sense for almost every t right off the bat. Okay. So how do we derive this? Well, the basic idea is to take our old friend the Bachner identity and apply the same rearrangement trick with the Gauss equation that Shane Yao applied to the stability identity. All right, and then our co-area formula also helps us along the way. So really what we want to do is take the Laplacian of the norm of our gradient 1 form, this norm of this harmonic 1 form, and integrate and see what we get. Of course, norm of h won't actually be smooth around critical points. So instead we take a little approximation here. Okay, so this is just a nice approximation of norm h. And if we plug in our Bachner identity, we see that this Laplacian of this approximation is bounded below by something like, something that looks like norm h inverse, some Hessian squared minus some d of modulus of h squared, plus this Ricci HH. All right, and the basic idea now is that this Ricci HH we can rewrite as a Ricci nu term, right? Because if we're thinking about our level sets, well, H is just a normal vector field, right? With this norm H weight out front. So in particular, we can rewrite this Ricci of HH as half norm H squared times exactly what we had before, right? So this ambient scalar minus the intrinsic scalar plus mean curvature squared, that won't drop out for us now, right? Minus second fundamental form squared, just the same Gauss equation trick that we learned from Shane and Yao, right? All right, and if we rearrange a bit and use the fact that this map is harmonic, so the mean curvature does have a special form, even though it doesn't vanish, then we see that we can rewrite this as half norm h squared, the difference of the ambient and the intrinsic scalar curvature, plus d modulus of h squared minus a half of this Hessian squared term, right? Well, in particular, since we only have minus a half of this Hessian squared term coming out here, that's going to cancel with only a half of this dh squared term out here, okay? And then this d modulus of h squared is going to cancel exactly with this d modulus of h squared here. All right, so in particular, where do we end up? We see that along regular level sets, because this only makes sense along the regular level sets, right? We can rewrite the Bachner identity in this form. So this Laplacian of this approximation of norm h is bounded below with some weight by this dh squared term plus the difference of the intrinsic and the ambient scalar curvature. All right, so all we've done so far is rearrange things a little bit in terms of the intrinsic geometry of the fibers. All right, now we have to be careful. So what we'd really like to do is just integrate this over our manifold where we're thinking of this phi delta as just being norm H. Again, we have to deal with critical points, so we have to be a little more careful. So we divide S1 into a V, which is going to be a large compact subset of the regular values, and some U, which is going to be a small open neighborhood of the critical values. Okay, and so we integrate this Laplacian over the manifold. We know that vanishes, and then we get the integral over the pre-image of that neighborhood of the critical values and the pre-image over this nice regular neighborhood here. Okay, and then we apply our coarea formula, right? So recall that for the coarea formula, we know that if we integrate some function f against norm of the du, right, this is the same as integrating over all the fibers, this integral f over the fibers, right? Okay, so in particular, on this set of regular values here, we can use this nice rearrangement of the Bochner identity. Okay, and we get this term popping out here by the coarea formula. And then for the critical values, we're just going to use the cruder standard form of the Bochner identity to say that we have this bound below by these Ricci terms. Okay, so where does that leave us? Well, let's see here. We say phi delta is an approximation to norm H. So as we take delta going to 0, this term here is just going to give us this dh squared with this h to the minus 2 out here, plus scalar curvature minus this r sigma, right? This term becomes 1 with v fixed, right? So in particular, this half scalar curvature integrated over this regular fiber, that's going to be, again, by Gauss equation, 2 pi times the Euler characteristic, right? And then we have these terms left over here, where again, we're fixing this nice compact set inside the regular values. Okay, but then these Ricci terms here, when we realize we can bound this whole thing below by just the L infinity norm of the Ricci curvature, right? And then the integral over this neighborhood U of the area of these fibers sigma t. Okay, so in particular, Sard's theorem tells us that we can take this measure of U arbitrarily small. And since the coarea formula tells us that the function setting t to the area of sigma t is a nice integral function, then we can take the measure of U arbitrarily small, and this identity leads us to just the identity we claimed to begin with, right? These terms, these U terms drop out as we take the measure of U arbitrarily small. Okay, so that's how we get to this main identity that we were looking at before. Okay. Okay, so now that we have this identity, what can we actually do with it? All right, so to begin, let's think about topological consequences of positive scalar curvature, right? One of the basic questions. Okay, so suppose that we have a closed-oriented three-manifold, and let's suppose that it contains no non-separating spheres. So if you hand me a two-sphere inside this manifold, it's going to bound some three-dimensional domain. It doesn't have to be a ball, right? We're not requiring that the manifold be irreducible, but it bounds something. It's homologically trivial. Okay, so at the level of prime decompositions, this is telling us that the prime decomposition of this three-manifold doesn't have any S2 cross S1 factors. Okay. Well, now suppose we have a non-trivial harmonic map from this manifold to S1. So we want to understand something about the structure of the fibers. Okay, so we know that the whole fiber represents this prescribed homology class, right? We know what homology class the fiber lies in because we know what homotopy class the map lies in. But fiber could have multiple components. So what can we say about the components individually? Well, we know at least that this gradient one form H is clearly going to be perpendicular to any component of a level set, right? Okay, but that also means that this Hodge dual star H is going to be a positive multiple of the area form along a level set. It's going to lie along parallel to the level sets, right? Okay, but the condition of being harmonic tells us precisely that this star H is a closed two form. So we have a closed two form, which is going to have non-zero integral over any component of a level set. But then by Stokes' theorem, this tells us that each component has to be non-separating. It can't bound some domain. Okay, so in particular, each component is non-separating. So if we're in one of these manifolds with no non-separating two spheres, well, then that means that each component of a regular level set has to have positive genus. Okay, so in particular, for any given fiber, we know that its total Euler characteristic is going to be non-positive. Fine. So in particular, our identity was framed in terms of this average Euler characteristic of the level sets. Well, now we know that that has to be non-positive, right? Well, that then tells us that this term on the right-hand side, this integral of these Hessian squared and scalar curvature terms, that has to be non-positive as well. Okay, so in particular, if scalar curvature is positive, and we have a non-trivial one of these harmonic maps floating around in such a manifold, then this would give us a contradiction, right? So parsing that out, this tells us that if we have a three manifold with positive scalar curvature and non-trivial integer homology in degree 2, then it has to have some non-separating two spheres. Okay? So, for instance, this tells you that the 3 torus can't have positive scalar curvature. Okay. So this gives us a simple Hodge theoretic proof of that fact. Of course, this is strictly weaker than this conclusion we quoted earlier from the minimal surface methods, right? So for instance, by the minimal surface methods, we showed earlier that not only do we have to have some non-separating spheres floating around in positive scalar curvature, but in fact, all of the degree 2 integer homology was generated by these two spheres, right? So, so it's a strictly weaker topological conclusion, and remember, even that was weaker than the original Shane-Yao conclusion about no incompressible surfaces. But nonetheless, it's this cute Hodge theoretic proof of the Garrosh conjecture. And of course, if we dig in a little more and make things quantitative, then we get some new information that we couldn't get from the minimal surface methods. Okay, so what do I mean here? So to this end, it's useful to recall this nice norm on homology, a nice topological norm introduced by Thurston. Okay, so if we have a class, a nice degree 2 integer homology class in a 3 manifold, then there's this Thurston norm, which is going to be measuring something like the minimum genus needed to represent that homology class by an embedded surface. Okay, more precisely, what we want is something like the negative total Euler characteristic of a representative, where we're throwing out spherical components. Okay, so for any connected surface, we're going to consider this quantity where if it has positive genus, we want to take negative the Euler characteristic. And if it's a sphere, we want to take 0. And then for any given surface, we introduce this measure of complexity called chi minus, where we say chi minus of sigma is just the sum of this quantity over all the components. So if a component is a sphere, we ignore it. And if for a non-spherical component, we add up minus its Euler characteristic. Okay? So, so it's telling us if we have no spheres, and this is just giving us minus the Euler characteristic. Okay, and then we consider the infimum of this quantity over all, or really a minimum because it's achieved, right? Over all surfaces representing this homology class. So that's just purely topological notion, but Thurston showed that it defined a nice semi-norm. Okay, so it's an honest semi-norm, and in particular, if there are, for instance, no non-separating spheres and no non-separating tori floating around, that's an honest norm. Okay? But anyway, it's a natural topological measure of complexity of a homology class. Okay, so in particular, if M contains no non-separating spheres, and we're looking at a harmonic map from M to S1, which is dual to some prescribed homology class, so its fibers lie in this class. Well then, since we just said there are no spherical components of these fibers, right, in such a manifold, well then this chi minus is exactly minus the total Euler characteristic of the surface. And so in particular, for any fiber, minus its Euler characteristic is an upper bound for the Thurston norm, okay, of this homology class. So now plugging in our identity again, where now we're flipping around the signs, right? We see that 2 pi times the Thurston norm of this homology class is bounded above by minus a half. Again, this Hessian squared term plus scalar curvature. And now we've undone our little co-area formula trick. So we're viewing this as an integral on M. And so we brought down a factor of norm du, right? We just undone our little co-area formula there. Okay, well then if we throw out this Hessian squared term and we apply Cauchy-Schwarz here, well then we see that this 2 pi times the Thurston norm of alpha, this topological quantity here, is bounded above by half the L2 norm of the negative part of the scalar curvature times the L2 norm of the gradient of u. Okay, and moreover, if we trace through what we've thrown out here, then we see that if equality holds, then the Hessian of u has to vanish identically. This is a totally geodesic map. And the scalar curvature has to be a non-positive constant. Okay. All right, but let's just note that this L2 norm of du, that's a natural geometric quantity. Okay, so in particular, this is the same thing as the infemal energy of all S1 valued maps dual to this, in the homotopy class dual to this alpha, right? Or if you like, it's the infemum of the L2 norm of any one form in the de Rham class dual to this class in H2, right? So it's a natural geometric measure of size of this homology class called the harmonic norm. Okay. So in terms of, with this terminology in place, right, we get this corollary, which is that if we have a closed oriented three manifold with no non-separating spheres, then for any non-trivial homology class, we have that 4 pi times the Thurston norm is bounded above by the L2 norm of the negative part of the scalar curvature times the harmonic norm of that class. And moreover, equality holds, keeping track of those little things we threw out, right? Only if M is covered isometrically by sigma times R, where sigma is some flat torus or some hyperbolic surface, okay, with constant negative curvature. All right, so what does this tell us, right? This is telling us that if the class is topologically complex, in terms of needing lots of genus to represent it, well then in fact the negative part of the scalar curvature has to be large in L2, right? So for comparison, if we were working with minimal surfaces, what we would see by plugging in our just stability identity and playing around, right, we would see that that the negative part of the scalar curvature would have to be large in L infinity. We'd have to have a lot of negative scalar curvature somewhere, namely along this area minimizing surface. With this harmonic form approach, we see that if we have a class with large Thurston norm, then in fact we have to have a lot of negative scalar curvature in a more global L2 sense. Okay, so slightly different information coming out. All right, what's perhaps more striking is that if we put in the slightly stronger assumption that the manifold is irreducible, so not only are there no non-separating spheres, but all the spheres bound balls, okay, well then the same estimate was obtained by Kronheimer and Rovka, except that they're phrasing it now in terms of dual norms on the degree 2 cohomology, all right, using machinery from Seiberg-Witten theory. Okay, this is back in the 90s. And it's really striking that you get the same estimates popping out because the techniques are really very, very different. I mean, they're, let's see, I mean, so they're considering these monopole classes, which have associated solutions of these Seiberg-Witten equations. And then you have some curvature 2 form associated with these solutions, which you then use as a representative of some degree 2 cohomology class. And you show that its L2 norm can be bounded above in terms of the L2 norm of the scalar curvature. Okay, and then you need to know some very delicate information that comes from some deep topological facts about how these monopole classes relate to the unit ball for this dual Thurston norm. There's a lot of deep stuff going on in there. And it's really strange that you get the same estimate, I mean, exactly the same estimate popping out from these two, at least superficially, very different techniques. Okay, so this is, I was just saying, it's striking that you get this same estimate popping out from these two techniques. And I mean, I certainly don't see any clear link between the two techniques. But if there is any meaningful underlying connection between the two paths to this estimate, then that would be very cool, right? Because then this would provide some relation between some small application of the Dirac operator methods and these level set methods, which are in turn pretty obviously connected to minimal surface methods. So any kind of connections you can find between these approaches would be very interesting. All right. Of course, unsurprisingly, you can also get more results from this that you can also get from minimal surface methods. And so one example of this is the following result, which follows from results of Bray, Brendel, and Neves. Okay, so if M is a closed oriented three manifold with non-trivial integer homology in degree 2, and suppose we have a positive lower bound in the scalar curvature. So just normalizing things, let's say the scalar curvature is bounded below by 2. Well, then if we consider a surface which minimizes area among non-separating surfaces, so we're thinking about the infemal area among all non-separating surfaces, that area has to be bounded above by 4 pi, and equality holds only if M is covered isometrically by a round sphere times R, by the cylinder over the round sphere. Okay, so in particular, we have this uniform area bound for the least area non-separating surface, as long as we have a lower bound on scalar curvature. All right, and then the only thing which achieves this bound is this round cylinder and quotients thereof. Okay. All right, so for this harmonic form approach, how do we see this? Well, since H2 is non-trivial, then there's a non-trivial harmonic map to S1, whose regular level sets consist of some number, we'll call it n of t, it doesn't matter, of necessarily homologically non-trivial, as we discussed before, connected components. Okay. Well then, for any such fiber, we know that the total Euler characteristic is bounded above by n of t times the Euler characteristic of a sphere. So in particular, it's bounded above by 2 times n of t. Fine. So then our average Euler characteristic is bounded above, or 2 pi times our average Euler characteristic, is bounded above by this quantity 4 pi times the average of this number n of t over S1, right? Well, that's in turn bounded below by this quantity we had from our identity. Okay, but if we throw out this Hessian squared term, and we recall that this RG is greater than or equal to 2, right? And this is bounded below by the integral over this t of the area of the fibers. This is bounded below by the average area of the fibers of this map. Okay, but if each fiber consists of n of t non-separating components, and A naught is the infemal area among non-separating surfaces, then each area is bounded below by A naught times n of t, right? Each component has area at least A naught. So in particular, we see that dividing through by our integral of this n of t, number of connected components, then 4 pi has to be an upper bound for A naught. And if we keep track of what we've thrown out, it's really immediate. Okay, we have a parallel one form. The scalar curvature is constant. So it's easy to see we have to be covered isometrically by this S2 cross R. Okay. Now, to get the area bound, so if we forget the rigidity statement, then this is equally easy from either the minimal surface or this harmonic form approach, right? The real advantage of the harmonic form approach is that the rigidity is spit out pretty directly by the fact that, just from this global estimate, we see that the scalar curvature has to be constant immediately if equality holds, and this parallel one form, that's a really quick path to rigidity. In contrast, I mean, the Bray-Wendell-Neves approach is very clever, and it's not, painful. It's, only 7 or 8 pages to get the rigidity statement. But nonetheless, it's non-trivial. It's not something that immediately falls out from just looking at the stability identity, for instance. So this is a mild advantage of the harmonic one-form approach over minimal surfaces, is that rigidity seems to fall out a little bit more easily in situations like this. All right, so we're starting to get the sense that these harmonic one-form techniques have some use at least. But one thing that might still be stuck in our teeth is that we're really sensitive to these non-separating two spheres. So in our applications to the Thurston norm or to other topological things, right, we keep having to impose this condition that we have no non-separating two spheres, and we're saying nothing about manifolds which have S2 cross S1 factors, right? So the question is, can we get around this? All right, and I mean, somehow the first answer is that no, if we're just using this identity from before. Okay, so suppose we want to show, for instance, that there's no positive scalar curvature metric on T3 connect sum S2 cross S1. Okay, so by minimal surface or Gromov-Lawson techniques, this is straightforward, but I claim that it's not going to fall out nicely from our identity. So why is this? Well, suppose we're looking at T3 connect sum S2 cross S1, and let's consider the following homotopy class of S1 valued maps. So we collapse our S2 cross S1 factor to a point. We get a nice degree 1 map from this T3 connect sum S2 cross S1 into T3. Okay, and now we take our favorite non-trivial homotopy class of S1 valued maps from T3 to S1, and we compose. Okay, so I claim, and it's not hard to show, that the associated homology class back in T3 connect sum S2 cross S1, it's not going to be representable by unions of spheres. Okay, so in particular by the minimal surface theorem we quoted at the beginning, right, you can see that we can't have positive scalar curvature because we have a class like this. Okay, on the other hand, suppose we're trying to show this with our little identity for the harmonic map. Okay, well, we can have the problem that maybe some of the fibers are tori, right? So those are giving us 0 Euler characteristic. But as we wind around, maybe some of the fibers look like a torus and a non-separating S2, which neither one of them is individually in the right homology class, but they sum to the right homology class, right? So the fiber is still in the right homology class, but these two components are not. Okay, and since we have a torus factor and a two-sphere factor, we're going to have positive total Euler characteristic. Okay, so in particular, even though none of the fibers is entirely made of two spheres, right, we can still have positive total Euler characteristic on average as we average over our fibers, right? So in particular, if this is the case, and this is a geometrically plausible setup, right? Then we can't rule out positive scalar curvature in sort of a straightforward way via our identity. Okay. So nonetheless, can we get around this non-separating sphere issue at all, for instance, to loosen the topological restrictions on these Thurston norm estimates? Right, and that brings us to some work with Hugh-Bray. Okay, so the idea is that ultimately we're going to want to do this by cutting away some minimal representatives of these non-separating two-sphere homology classes and apply techniques on manifolds of boundary. So how does this go? All right, so suppose we have a compact oriented three manifold of boundary. Well, now we again have that the homotopy group of S1 valued maps, or group of homotopy classes of S1 valued maps, is isomorphic in a natural way to the degree 1 cohomology with integer coefficients. And now Poincare-Lefschetz duality is telling us that that's naturally isomorphic to the degree 2 homology relative to boundary. Okay, and again, this map from S1 valued maps over to the homology is just given by taking level sets. Okay. Okay, and similarly, Hodge theory on manifolds of boundary tells us that we're always going to have an energy minimizing representative of any one of these homotopy classes, okay, whose gradient one form H will be harmonic on the interior, and on the boundary satisfies this homogeneous Neumann condition. So H is going to be parallel to the boundary of our three manifold. Okay. All right, so for such an energy minimizing map, we have the following generalization of the original identity in the closed case. And unsurprisingly, the new thing that shows up is just a little mean curvature on the boundary. Okay, so what we get is that this average Euler characteristic is bounded below by, well, the same thing we had before on the interior. And then on the boundary, we have the mean curvature weighted against the norm of the gradient of this map. Okay, so of course, anyone who spent some time playing with scalar curvature on manifolds of boundary, it's not at all surprising that we have mean curvature showing up on the boundary here. But it's nice that the identity works out so cleanly. And it's the same kind of procedure from before. The computations just line up nicely on the boundary. Okay. So now what can we do with it? Well, the main application we had in mind was not to the manifold of boundary case, but to, in fact, the closed manifolds, where we're using the manifold of boundary results to apply the chopped up versions of our original closed three manifold. So in particular, we're able to extend this Kronheimer-Rothke relation between the Thurston norm and the harmonic norm to arbitrary closed-oriented three manifolds. So for any closed-oriented three manifold and any homology class in H2, we have that 4 pi times the Thurston norm of alpha is bounded above by the L2 norm of the negative part of the scalar curvature and the harmonic norm. And I neglected to mention before, but this is always sharp in the sense that for any homology class in any manifold, you can find a sequence of metrics exhausting this, right? Okay, and moreover, if alpha can't be represented by spheres and equality holds, then you can show that M is covered isometrically by a cylinder over some flat or hyperbolic surface. Okay, so what's the idea? Well, now we bring in a little minimal surface theory. Okay, so by results of Meeks and Yao, some deep results, there's going to be a disjoint collection of, let's say, K, some number of embedded minimal two spheres, generating the spherical portion of the homology. Okay, so we're taking the portion of homology generated by non-separating two spheres, and we're saying we can find a collection of disjoint embedded minimal two spheres that generate all of this homology. Okay. Okay, and now we can cut along these spheres. So we're not cutting the manifold into pieces. We're literally just cutting and saying, okay, let's declare that what was once connected here is now two boundary components. Okay. And now we get a new manifold with 2K minimal boundary components. Okay, and it'll have the property that there are no non-separating surfaces, no non-separating now in the relative homology sense, of positive Euler characteristic. Okay, and then the game is, okay, well, there's a natural map from H2 in our closed manifold to the relative H2 on this manifold of boundary. And with a little work, you show that it decreases the harmonic norm. That's pretty straightforward. And you see that it doesn't decrease the Thurston norm. Okay, and then you apply this identity for manifolds of boundary to this new cut-up manifold N, and it's not hard to see that you get this nice estimate for the original man. Okay, so I'm skipping over most of the details there, but you can look at the paper. It's not too difficult once you see the path. Okay. All right, now given the kind of applications that I've been advertising so far, it probably won't be surprising that the same techniques have something to say about general relativity. And in particular, with Hugh Bray, Dimitri Kazaris, and Marcus Curry last fall, we were able to apply these techniques to get a new proof of the three-dimensional positive mass theorem using harmonic functions. And I think I'm going to breeze through this next part because Dimitri Kazaris is also going to be giving a talk in this workshop where he's going to discuss in depth the applications of these level set methods to the study of mass and general relativity. So I'm just going to skip over this. But the point is we're able to get a nice S2 of explicit lower bounds for the ADM mass via harmonic coordinates, which are on the one hand reminiscent of Witten's integral characterization of the ADM mass via harmonic spinors. But on the other hand, the level sets of these harmonic coordinate functions, we're kind of using them in the same way that that Shane and Yao used their minimal hypersurfaces in their original contradiction proof of the positive mass theorem. So again, it's this weird double life where it has this geometric flavor at the level of intuition, reminiscent of the Shane-Yao minimal surface story, but it spits out this global formula in terms of this linear elliptic PDE that looks a little more like what you get by working with spinors. It's this funny space in between that it occupies. All right, so that's this new proof of the Riemannian positive mass theorem in dimension 3. Dimitri will talk about that in detail in his talk. I encourage all of you to watch it. Okay, and in the months since, again, Dimitri will talk more about this, but there have been some other fun contributions in this direction. So in particular, Pengzi Miao gave a new interpretation of these results by relating the ADM mass to computations on large coordinate cubes. And this also kind of ties in with things that I believe Chao Li will be talking about, polyhedral rigidity and scalar curvature. And then Sven Hirsch, together with Dimitri Kazaris and Marcus Curry, were able to adapt these techniques, not with harmonic coordinates, but with a slightly different equation, better adapted to non-time symmetric initial data, to get a proof of the full space-time positive mass theorem. And I won't get into how that goes, but again, I think Dimitri is going to give a nice treatment in his talk a different time in the workshop. All right. All right, but for now, let me just leave you with a few final thoughts. So the first is that this Bachner plus co-area path we took to get to the original identity, it's not the only path there. All right, so at least formally, we can make the following computation. So as we're moving along the level sets of a harmonic function or a harmonic S1 valued map, right? Well, then by moving along level sets, we're always moving with speed 1 over the norm of the gradient, right? And so just taking advantage of the way that curvature appears in the linearization of the mean curvature, so the same computations we're using to get, for instance, the stability inequality for minimal hypersurfaces and so on. Well, then we can check that the derivative of the integral over the fibers of this norm of the gradient times the mean curvature, well, it's exactly this thing that we wanted to integrate to 0, right? It's this half the integral of this Hessian squared term plus the ambient scalar minus the intrinsic scalar, right? So at least formally, we could integrate this over S1 and get the same identity we were playing with before. Okay, so the fact that we're using now the linearization of the mean curvature and derivatives of some quantities over these level sets, this makes it a little clearer. This is a natural cousin of both the minimal surface and the inverse mean curvature flow methods in dimension 3. So in particular, if we're playing with inverse mean curvature flow, well, then in the level set formulation of Huisken and Ilmanen, this norm of the gradient will be exactly the mean curvature. That's the level set formulation of the inverse mean curvature flow. And then what we're differentiating here would just be the mean curvature squared. Okay, so in particular, the exact same kind of computation leads you to the monotonicity of the Hawking mass along inverse mean curvature flow, right? Which is the key feature, which is why it's such a powerful tool in dimension 3. All right, and similarly, we can view the minimal surface approach as sitting inside this family, this larger family of level set methods using the geometry of distinguished foliations in dimension 3 to probe the scalar curvature. So these harmonic level set methods really sit inside this larger family, which includes at its boundary the inverse mean curvature flow and the minimal surface methods. And so already in this work of Hirsch, Kazaris, and Curry, we've seen another instance where applying them to a slightly different PDE gives nice information in terms of the space-time positive mass theorem, for instance. Okay, so the harmonic business is just because, you know, harmonic functions are baby's first PDE, and it's a natural case to look at first, but it's certainly not by any means the only place to look. All right, so if we have this nice large family in dimension 3, the question is, do we have anything nice along similar lines in higher dimension? And this is kind of, I think, a large and maybe difficult question. Okay, and note that when I'm talking about sort of a generalization of these methods to higher dimension, I really don't mean some kind of nice straightforward analog of these computations we're doing in dimension 3. But more broadly, I'm really interested in the following. Okay, so in dimension 4 and above, for instance, is there any useful relationship between scalar curvature and the intrinsic geometry of the fibers of some distinguished maps to S1? Right, so I mean, in some sense, the minimal hypersurface methods are one positive answer, because they're, if you try to minimize the L1 norm of the gradient in the homotopy class of S1 valued maps, you end up with this degenerate problem where you just get the fibers collapsing to the area minimizing representative of that homology class. Okay, so in some sense, there's a boundary case of this, which is already the minimal surface method, which we know works in higher dimension. So the question is, are there any non-degenerate variational problems in the homotopy class of S1 valued maps, which give you something useful about the scalar curvature in higher dimension? So for instance, with harmonic maps to S1. Now you can always make some computations in which the scalar curvature appears, right? But I mean, a good first test for whether this is useful is whether, for instance, you can use it to recover something like the non-existence of positive scalar curvature on the N-torus by new methods. Okay, so broadly, is there any distinguished fibrations, singular fibrations, which provide useful information about the scalar curvature? Alternatively, maybe instead of looking to S1 valued maps, it might be more natural to look to maps to Tn-2, right? Certainly in the applications, these show up a lot. So maybe that's the appropriate generalization. So if there's some nice distinguished, and again, I'm open to very broad interpretations of distinguished here, but there's some nice PDEs for maps to Tn-2, such that the topology or geometry of the fibers tells us something useful about the scalar curvature. And I think any progress in this direction would be really nice, because with, our minimal hypersurfaces and our Dirac operators, these are very powerful tools. We can do a lot with them, but we should continue looking for other tools for probing the scalar curvature. That's all. Okay, but for now, thank you for watching. If you have any questions, please feel free to email me. And yeah, stay safe. Have a good time. Bye-bye.